So as you've seen previously, the cell membrane and its membrane protein, specific membrane protein, set up chemical gradients for a variety of electrolytes, ions. One very specific example that we've seen before would be the sodium potassium pump, which sits here in the membrane and moves sodium out of the cell and potassium into the cell. Now, there are a variety of other transporters we'll see in other figures and videos. But suffice it to say, there's a variety of gradients across the membrane for particular solutes. Now, those solutes would tend to diffuse down their gradients based upon, that the fixed law, right? The diffusion of things from higher concentrations to lower concentrations. Of course, we have to have a pathway for these hydrophilic solutes to do so. But given a pathway, they would tend to diffuse from a higher concentration to a lower concentration. However, there is one additional component we have to worry about when speaking about the diffusion of ions, and that is the presence of their charge relative to the charge of the inside of the cell membrane. Right? And at rest, the inside of the cell membrane tends to be negative, right? This RMP, resting membrane potential, is negative inside relative to outside. We could just as readily put plus signs on the outside here too. Now, having said that, we have two driving forces on any particular ion across a membrane, assuming there's a gradient in their concentrations. That is, for sodium, for instance, right, we just said that the sodium-potassium pump is moving sodium out, so there's a lot more sodium on the outside than the inside of the cell, and it therefore has a chemical gradient that drives it into the cell. Well, we can't assume that sodium will enter the cell just yet because we also have to account for its charge relative to the inside of the cell. Now for sodium, this is quite easy because opposites attract, and a positive ion would tend to be attracted to the negative inside of the membrane. And so the electrical gradient is also inward, which means the summative force, the sum gradient on sodium, the electrical and the chemical gradients added together, also known as the electrochemical gradient, would be inward. If we look at calcium, it's the same situation. Higher concentration outside, chemical gradient inward. It's positively charged. Inside of the cell is negative. And so both chemical and electrical gradients drive it inward. Electrochemical gradient is the determinant of which way the ion will move. And so we have inward flux if we're given a permeability. Now we get to the two trickier ones. Chloride is in higher concentration outside the cell, and therefore its chemical gradient is inward. However, it is negatively charged, similar to the inside, and so it is repelled from the inside of the cell, right? So now we have a situation where we're not sure exactly which way this ion will move. And we're going to need another piece of information to figure that out. It's called the Nernst potential or the equilibrium potential. And it's the point at which these two gradients are equal and opposite. And at that membrane potential, because the chemical gradients are fixed, chemical gradients really do not change dramatically. I always say there's a name for cells in which the chemical gradients have changed. Dead. Right? Chemical gradients remain very stable over time. We regulate these ion levels quite strongly. And so modifying them dramatically usually causes sort of catastrophic events. So we need a little bit more information to determine which way the chloride ion would move because we have oppositely directed gradients. And we'll get to that a little bit later. Again, we could go over to potassium, and it's another similar situation. It's higher in concentration on the inside now, the one oppositely directed chemical gradient. But of course, it's positively charged relative to the negative inside of the cell, and so it has an electrical gradient inward. And so again, we might not know which way it's going to move. I do have the arrows showing the chemical gradient being larger here, and that's going to indicate which is the winner under most circumstances, the winner between chemical and electrical gradients. And again, it's important to note that chemical gradients tend to be relatively stable, Whereas electrical gradients, especially in excitable cells like neurons or muscle cells, can change because the inside of the cell can actually become less negative or even positive, flipping electrical gradients. That's where it'll get tricky, and we'll bring that up in another figure and video.